Let's begin then. Starting today, we will discuss about matrix eigenvalue.
Okay.
But don't forget about the materials from chapter 7, okay, because they are related with this chapter 8. These are the topics that we will discuss. The definition of eigenvalue, eigenvectors, physical interpretation, and then how to use the eigenvalues to solve differential equations. Anyone know what is eigenvalue? Never heard of that?
Never.
In beam problem?
Beam.
Huh?
I've heard it in the joke.
Let us start with the definition, okay? We discussed about this case for 2 weeks already, yeah? Ax equal to b, and then you learn about how to find x for 2 cases, okay? The first case is when a is singular. Another case is when a is non-singular, a has inverse. When a is singular, then you have to find out ax equal to 0 and also the other particular solution, okay? But then especially for ax equal to 0, if we use the answer to be x all 0, okay, I said last time it is called the trivial solution. Okay? Trivial means not interesting, not so important. So for this kind of problem, we want to find out non-zero x that can make this to be happen, okay? And it can only happen when a is what? We have non-zero x for this when a is singular. Yeah. So this equation ax equal to 0, we can find the solution non-zero x only when a is singular. Okay. A has no inverse. Determinant a is 0. Okay. A is not full rank. Okay. Let us list all of those definitions. Okay. These are equivalent. A singular. It is equivalent to A inverse not exist. Okay, determinant A is 0. What else? Not with transpose. Okay, not full rank. What else? What else? Huh? Linearity. What about the linearity? Huh? A non-linear?
Not independent?
Yeah. Columns of A are not linear independent. Okay. Column or rows not linear independent. Okay, at least we have all of these equivalent condition, yeah. Then if this happen, that means for ax equal to 0, we can obtain x to be non-zero. Okay, we can surely find a solution x non-zero for this problem. Okay, and we will use this property to find out the eigenvalue. Okay, let us define first what is eigenvalue. Okay. Lambda and v we call lambda and v to be eigenpair. Okay, lambda is eigenvalue V is the eigen what? Eigenvector. The eigenvector. Okay. Okay, let me write down this eigenvector. If a v of this is of a, okay. If this is holds, yeah, v is a vector, then both lambda and v are the eigenpair of a. So that means lambda is eigenvalue of a, v is the eigenfactor of a. So this is the condition. Yeah. From the point of view of this equation only, what can you tell about eigenvalue and eigenfactor in this case? You have a matrix. Let's say you have a matrix 1, 2, 3, 4. When you multiply this matrix with a vector, let's say v1, v2, then the result is like this. Eigenvalue is a constant.
Represents.
Have you ever heard about if I multiply, let's say I have a scalar 5, okay, 5, scalar 5. If I multiply this scalar by a constant, what will I get?
A times 5.
It is a times 5, right?
Yeah.
Okay. So you can see if you multiply a matrix by an eigenvector, or I should say, if I pre-multiply an eigenvector by the matrix itself, what I will get is that the same vector, but with a scaling. The scaling is the eigenvalue. Okay, this is the scaling. The lambda can be 0, can be 0.1, can be minus 10. It can be complex number. Okay. So this eigenvector, you can think of it as a direction. It is a direction that will not change. This one will not change. For that matrix, this direction will not change. Okay. Well, why is that so? Because when you multiply a matrix by its eigenvector, you will get the same eigenvector but with some scaling. Yeah. An example, if let's say we have an eigenvector of a matrix which is this one. Okay, let's say this is 1 and this is 2, let's say, yeah. So 2 to the right, 1 above, okay, like this. If we multiply this vector using the matrix and this is the eigenvector, what could happen is that either we get this one, so the lambda is bigger than 1, or let's say lambda is less than 0. Okay, so it goes this way. It's a reflected vector. Okay, if let's say the lambda is less than 1, between 0 and 1, then you get a shorter vector, short one. So the eigenvector here defines the direction. It gives you the direction. Yeah. Okay, so these are the physical meaning. Okay, mathematically we will only work with this, and that's the main task in this chapter. Yeah, the main task in this chapter is this one. Okay, is to work with this. How do we find lambda? How do we find the eigenvector? That's our job. Okay, and discussing this is just the physical meaning of it. Any questions so far? Okay. So as I said earlier, we have the ax equal to lambda x in here. The eigenvector is denoted as x, but we can use any variable. Yeah. Okay. So what we can do if we want to find out x and lambda is that we can move this to the left side. Okay, let's move them to the left side. So what we'll have is a minus lambda I times x equal to 0. Anyone wondering why the identity matrix comes in? Anyone know why? Why suddenly we have identity matrix? Or, yeah, it's correct, sir. Nothing to ask. Are you okay with that? Or are you not okay? If it is okay for you, then I don't have to discuss. Ah? Anyone else?
I don't know.
Only one person questioning why there is an identity there. So the rest of you, the remaining of you, you know what's the reason? Huh? Yeah? Not sure? You don't find this to be troublesome for you?
Troublesome.
From here to here, you don't find it troublesome? Well, it's good. It is. If it is not troublesome, it's good. Okay. Yes, that's correct. Yeah. Subtraction of a matrix, you have to get a matrix with the same size. Okay, so lambda you multiply with identity, so that what happened actually when you do this? This is when you have a for example, yeah, square matrix minus lambda times identity, all 0. It's like this, yeah. A minus lambda I is like this one. We have random matrix A minus lambda times identity. So what you will get is A11 minus lambda, and then this is A12, A1n, this is A and n minus lambda, and then the rest are the same. Okay, like this. Good question. Eigenvalue is only discussed for square matrix. Okay. Does rectangular matrix, non-square matrix have eigenvalue? Yeah, we cannot compute the determinant. So in advanced course, you will find what we call as a singular value. So let's say if B is not square, yeah, not square matrix. What you will find instead is a singular value for B transpose times B. So this matrix will be rectangular. Will be square. Okay. Then after that, you find out its singular value, not eigenvalue, but we call it singular value. So eigenvalue is only for square matrix, yeah. Okay, now you know this one can only have a solution for non-zero x if what? A minus lambda x, yeah, x is non-zero only if what? Which part is singular? Is it A singular? Any other answer?
Lambda kan nggak mungkin, dia kan lambda kan konstan.
I repeat again, yeah, the concept here. You forget, now you forget already. the problem of ax equal to 0 has non-zero x as the solution only when a is singular. Okay, a is singular. So in this case, which matrix that is singular?
A.
A minus
A
lambda.
minus lambda.
A minus lambda I. Okay, not the a, but a minus lambda I. Yeah. So this is the singular matrix. Okay. This has to be singular for you to gain non-zero x as the solution. Okay, you listen me carefully, yeah. In some definition, lambda is also called as a variable that reduces the rank of a. A variable that can reduce the a rank. Okay, you get what I mean? When you plug in lambda into here, then suddenly the resulting matrix is not full rank. Okay. Wait, sir. Is singular matrix bad, sir? Isn't it bad? Right? Determinant 0, we don't want it, right? Like, 0 is not good. So, is this okay, sir? Anyone think that in that direction? No. No, you must not think like that, okay? This is the fact, the reality that we have to face. Okay? Okay, and this is okay. This is perfectly fine. And from this equation, we will find the lambda and x. Okay. So some comments that in here. The first one is a good comment. An eigenvector is just a vector in the null space of A minus lambda I. Yeah, that's correct. Okay. Yeah. So now, if I ask you, yeah, we have this equation here, yeah. We have this equation here. If this is true for A, and we have non-zero x as the solution, what will be the eigenvalue of A? Can you tell one of the eigenvalue of A? Just one of them is okay. No. No. Not one. You say that. Louder? Zero. Okay. If you find out that this is true, then 0 is an eigenvalue of A. Why is that? We use this. Yeah, you plug in 0 here, you get 0, right? So 0 is an eigenvalue of A if this one holds. You get that?
Yeah.
Okay, so we now add the list, yeah. A singular, determinant A 0, A inverse not exist, some of them, and then 0 is an eigenvalue of A. Okay, this is an equivalent condition to that. Yeah, we add the list of the equivalent condition. Okay, so now can you prove that when determinant of A is 0, then 0 is an eigenvalue of A? Can you prove that?
Determinant is 0. 0
Yeah.
is the eigenvalue of A.
Yeah, or the other way around. Or when 0 is an eigenvalue of A and then A is singular, A has no inverse. Can you prove that? Homework, yeah. You think about that. It's a classic proof on math. You will find that on the homework chapter 8 also. And not this particular problem, but there will be some classic proofs on eigenvalues. Okay, any questions so far? John? I discussed this just now, yeah, about eigenvector is a direction. Okay. Exercise. So this one is coming from your homework. Problem number 1, true or false? Trivial solution x equal to 0 to the eigenvalue problem is an only eigenvector if it corresponds to the eigenvalue lambda equal to 0. At
It's equal to 0. The problem A. No? False.
You said false. Is it true? What's the reason for true? You plug in 0, eigenvalue is 0. But what about the x? Is x also 0? No, so the statement is not true then, in that case, yeah. Because the false statement coming from here, yeah. Even if the eigenvalue is 0, then x cannot be 0. Okay. What does it mean? I'm saying that when lambda is 0, x cannot be 0. But when x is 0 is the only possible solution to this. Let's say, if the only possible solution to this is x equal to 0, if I'm saying, yeah, if the only possible solution to this problem is x equal to 0, then the other way around, 0 is not eigenvalue of A. Okay? You get what I mean? Previously, I'm just reversing the statement, yeah. If x equal to 0 is the only solution to this, then 0 is not eigenvalue of A. Is this okay? Brian, okay, Brian? Yeah. Problem number 2. If lambda is an eigenvalue with corresponding eigenvector v to x equal to max, then the normalized eigenvector is also an eigenvector to eigenvalue lambda. Is this correct? Normalized means you are taking the unit vector of the eigenvector. Let's say if this is true, yeah, then I write down A of uv. Uv is the unit vector of v. This is equal to lambda times uv. Is this also true for the unit vector of the eigenvector? If this is true, does this holds true also? Should be, not sure. What's the reason for true? Huh? Which factor you said? Which factor that you are talking about? The statement is true. This is true, yeah. The normalized eigenvector is also the eigenvector. Why is that so? Because the eigenvector is just a direction. Okay, it's just a direction. If let's say we have an eigenvector of 1 and 2 like this. Okay, and then we have a1, a2, a3, a4, and this is equal to lambda times 1, 2. I don't know what's lambda, but if this is true, then you can plug in 0.51 lambda, 0.51. Okay, even if this is not a unit vector, yeah, this is just a fraction of that. Okay, because this one have the same direction of that eigenvector. Okay, so the most important thing on eigenvector is the direction, not the value itself. It's the direction. Okay, So if right on here, yeah. If y is eigenfactor of A, then alpha y is also eigenfactor of A. Okay? For alpha real number. You get it? You are late, so you don't know what's going on, right? Okay. So if we have ay equal to lambda y, then A times alpha y is also, this one is also true. Okay. Why this is the same with the above? You can cross alpha, right? This is just a constant. Okay. You still don't get it? Or you get it? Okay, we will prove with the quiz next week whether you understand or not. You don't want? But that's okay. Yeah, this is a bonus point.
Quiz okay.
Okay, the next problem. Eigenvalues and matrix addition. This A and B is a square matrix. Eigenvalues of the sum A plus B always equal to the sum of eigenvalues.
Eigenvalue of A and B.
Yep.
A plus B is equal to the eigenvalue of A and B.
Okay, you scribble on your notes, yeah. Find out whether this is true or not.
No, it's not. Plus B sama dengan A atau B?
Tidak lah.
Lo yakin?
Eigenvalues of A.
The eigenvalue of the sum of A plus B.
Let's say C is A plus B, okay? And so from this we get Cx equal to lambda times x,
Okay.
where this is A plus B lambda times x. And then on another note we have AXA equal to lambda A XA. Okay, and then B times XB lambda B XB.
Okay.
So the question asking you that, is it true that lambda is equal to lambda A plus lambda B? Is this correct or not? That's the question.
Oh.
Do you get what I mean? Yeah.
Kan? A plus B sama dengan lambda A plus lambda B.
Okay, you know what's the question already, right? Okay, who don't understand the question? Michael, do you understand the question? Sean, you understand the question?
Beda.
You don't? Which part you don't understand?
Kan
I'm asking about the question, not the answer. Do you get the question?
Oh. So ini kalau lambda A sama lambda B.
Yeah.
Lambda A sama
Eigenvalue of the sum, that's it the same with the sum of the eigenvalue. Okay.
Oh.
So I will leave this for you to think on your own, yeah, because this is a good practice for you. Next Wednesday. On Wednesday we'll back to this. Okay, you think about it. Thursday.
Yalah. we are taking other class.
Wednesday, yeah.
Menyusun.
Okay, now let us discuss about computing the eigenvalues and eigenvectors. In MATLAB, you try, it is false. And now you have to prove.
Kita mesti approve.
No, I mean, saying the statement is not true by plug-in numbers is really not respectful to the statement, you know. You have to show respect by showing a neat proof, yeah.
Proofnya apaan tuh?
And this is a sentence, not just a equation. Okay, now we will discuss a method on computing the lambda and x. Okay, so this is the original equation that we have, and then we move lambda x to the left side, so we have a minus lambda I times x equal to 0. So we want to find out non-zero x so that this is happen, yeah. So in this case, a minus lambda I has determinant to be 0, correct?
Yes.
Yeah, so the determinant of a minus lambda I is 0. Then we will exploit that fact. We compute the determinant of that where it has lambda on it, then compute the lambda based on the polynomial. Okay, we take the roots of the polynomial.
What?
We compute the determinant of that. But
Of a minus lambda I.
That's
Singular.
singular.
Yes.
Okay.
We know that the determinant of this is 0, right?
Okay.
Determinant of lambda I.
Iya kan singular.
Singular, so the determinant is 0, right?
Yeah.
If the determinant is something else, we cannot compute at all. Yes. So we will exploit the fact that the determinant of a minus lambda I is equal to 0. No, we know it is 0.
Yeah.
You just have to expand, then you will find polynomial in lambda. Yeah, you have polynomial in lambda equal to 0, then you find out the roots of this equation, you will get lambda. Okay? You get the idea, yeah?
Jadi kuadratik.
If it is 2 by 2, it is quadratic. Okay, if it is 3 by 3, you have cubic polynomial. 4 by 4, you have lambda to the power of 4.
Secara kompleks.
It can be complex. It can be complex. Okay, yeah. So that's the plan. We compute the determinant of this, but we know that the result is 0. Okay. Yeah, the same step. We skipped it. Okay, an example. Example is that, of course, this format we already plug in a minus lambda I. Okay, a minus lambda I times x. Then we get this. But I will just explode what is a in here so that you know what happened. Michael, you pinching just now. What happened with you, huh? You are thinking, trying to understand what's going on. So in that case, we have a to be 10 minus 5 minus 5 and then 10. Oh, this is a symmetric matrix. Okay. So a minus lambda I is 10 minus 5 and so this is equal to Okay, like this, yeah, correct. And we want to expand into a minus lambda I x equal to 0, right? So this is in here. You know what happened? This, right? So this is 0, and then minus 5x1. Yeah, they are the same. Yeah. Okay, now to compute the lambda, get the determinant of this. What's the determinant of that?
1 over a
Multiply this minus multiply of that. Okay, so the determinant of a minus lambda I in this case is 10 minus lambda square minus of minus 5 times minus 5. So you have I squared it and then minus 25. Yeah, and then the result is 100 and then minus 20 lambda. Yeah, you have 100 minus 20 lambda plus lambda square minus 25, and the result is
lambda square minus 20 lambda plus 75.
okay. So we know using that already, yeah, we can expand this as lambda plus 5, no, lambda minus 5, because this is minus, yeah,
Oh, minus lambda
minus 5 times lambda minus 15. So we know that one of the lambda is 5, the other one is 15. Okay, if you can factor it out by just inspection, yeah, you just do it right away. If it is too hard for you, you use the ABC formula for the 2 by 2 matrix. Yeah, is this okay?
Yes. For now, yes.
You don't like the ABC formula? You try out something else. There are other brand other than ABC, right? ABC what? ABC.
Really?
Right.
Yeah.
Yeah, we have other.
I only know ABC.
Yeah, quadratic formula. Yeah. You don't know? Okay, let us define it lah,
Yeah.
so that it is not ambiguous. Okay.
Yeah. Kurang popular, no? It's popular.
Okay, lambda 1, 2 is 20 plus minus square root of minus 20 square minus 4 times 75, and then you divide by 2. Okay, so we have 10, this is plus minus half. Okay, this is 400 minus 300, and plus minus half times 100. 10, yeah, 10 times half, so it's 5. So we have 5 and then 15 this case.
Oh.
Okay, any question on this? Easy, yeah. Now how do we find the x1 and x2? We know that it is 5 and 15. The next question is how to get the eigenvector. Okay, substitute the lambda equal to 5 and then find the x. Another, we substitute lambda equal to 10, then we get another x. This is quite tedious, yeah? Tedious work. Okay, pay attention. Attention.
Yes, sir.
Okay, yes, sir. Lambda equal to 5. Then you plug in here. Put lambda equal to 5. What? From what movie is that? From what movie is that? Sorry, yes, sir.
All military.
Huh?
All military movie.
All what?
Military movie.
Every
Oh, all of them
type
like that.
movie have that.
Okay. Now I'm the general. You are the soldier then.
Yeah.
Yes.
Sorry, yes.
Yes. So you plug in lambda equal to 5 here. What do you get? 5.
Minus 5. Minus 5. 5.
Okay, and this is. So in this equation, from the first equation, you get
8.
5x1 minus 5x2 is equal to 0. So in this case, x1 is equal to x2.
Yeah.
Yeah, that means our first v1 is just 1 times alpha.
1 times alpha.
Yeah, the direction is 1 x1 is equal to x2, right?
Yeah.
Or slowly, if it is slowly, yeah, slowly we say x1 is equal to x2, so x2 equal to x1, right? You can say x1 or x2. Okay, and then take out x1 1 or x2 1. Now in this case, because eigenvector is just a direction, does x1 and x2 matter? No, right? So we can write down an alpha 1. Finish. Okay, because we only need the direction. Okay. Now when lambda is equal to 10, what happened? 0 and 0. Okay, x1, x2. Yeah, bear in mind, I'm not using the second equation because the second equation is just the same.
Yeah.
We get the same direction. Yeah. If let's say you are curious, using the first equation, using the second equation, you get different direction. One of them must be wrong, or both of them could be wrong.
How to know, sir?
Huh?
How to know which one is wrong?
Which one is wrong? Yeah, see carefully. Ask your friend, is it correct or not? Okay. This is 0 times x1 minus 5x2 equal to 0. Okay. So in this case, I can choose any x1. Yeah. Not choosing any x1. Sorry. So minus 5 x2 is equal to 0. Then in this case, x2 must be 0.
Yeah.
Okay. So in this case, our v2, I can choose x1 and this has to be 0. Or alpha 2, 1, 0. This is the eigenvector.
What is the value for x1?
Huh? Any number. we only find from here that x2 must be 0. x1 is free to choose. Yeah.
0 x1 sama dengan 0. 0 x1 sama dengan 0.
Michelle, are you okay, Michelle? Is this fine? Can you see clearly? Why are you all sleepy today?
Can you visualize it?
Huh?
Sir, I'm still
Can you
confused.
visualize it?
Which one?
Sorry, what if we use the second line, the second rule? Isn't it gonna be like inverse then?
If we use minus 5x1, 0 times x2, then you will find out that in here x2 is free, and then x1 is 0. Okay, yeah, for especially for this case, you will have v2 to be let's say alpha 301. Okay,
So there will be two value of V2.
wait, let me check, yeah. Let us plug in the solution. Is 10 minus 5 minus 5, and if I multiply with 1 0, what do we get? 10 10 and minus 5, yeah.
Okay, so
Wait. You made it wrongly lah. 10 minus 15, you know. 10 minus 15 is minus 5, not 0.
minus 15.
15. Oh, X. Lambda is not equal to 10.
Lambda is not
not equal
10.
to 10.
It's 15.
15.
That's the mistake, okay? So you see, when something is not right like this, something must be wrong, okay? Yeah, it's not possible that this thing can happen different direction.
Yes. minus 5
Why don't anyone remind me on this? This is 15, not 10.
I remind you.
You don't remind me?
Wait, we wanted to test this one.
No. This is not intentional. But I give you an example when something goes wrong, you know what to do lah. Okay? This is not right. Something is not right. You check. Oh, not correct. Okay? Now, even if you make a mistake, you still have to keep your common sense. Okay. So this is minus 5. Yeah. What happened in here is that I can see directly that the V2 must be alpha 2 1 minus 1.
Yeah.
Okay. What if it is minus 1 and 1?
Yes.
Are they the same?
Yeah.
The same, yeah. Yeah, just the other one go to the other quadrant lah. Yeah.
So apa ya kalau dia ke mirror?
Yep, mirror they're still the same.
You want
This V1 like this, yeah. And then V2 is going this way. Okay. Yep. This is V1 and this is V2.
Wow.
itu representing apa? What does the line? What is the line?
The line represent the vector itself. The vector itself where you multiply this by any kind of number. Okay. It defines the directions. Eigenvector is a invariant direction of a matrix. Invariant means that doesn't change, not varying. Okay, let us test for the last time. We have 1 and 1, yeah. 10 minus 5 minus 5, 10 multiplied by 1 1. What do we get? 10 minus 5. So it is 5, yeah. Minus 5 times 1, 10 times 1. So it is also 5. Correct? So what is the this is now 5 times 1 1, correct? Yeah. This is correct. 10 times this, 5, we get 5, minus 5 times 1, 10 times 1, we get 5. Yeah, 5 is equal to 5 times 1 1. Yes. So we have 5 to be the eigenvalue. Okay. this is lambda equal to 5. Now, when lambda equal to 15, we have 10 minus 5, 1 minus 1. What do we get? 10 and then 15, yeah? So where is the eraser? 10 plus 5 in this case. So we have 15. Minus 5 times 1, 10 times minus 1. So it is minus 15. And this is equal to 15 times 1 minus 1. Okay? So we get the eigenvalue 15. What if we multiply with minus 1 and 1 instead? Minus 1 and 1. What's the result? Minus 10, minus 5. So it is minus 15, yeah? Minus 5 times 1, 5, and then this is 15. So this is still the same, 15 times minus 1 and 1. Same eigenvalue. Okay? Any questions so far?
Yes.
Okay, following this method, you can compute eigenvalue and eigenvector for any kind of matrix. Okay? The next topic in here, okay, this is about the direction. Okay, you compute this. Now you compute. We still have 15 minutes. Practice. The one who get correct, I will add one more point to the quiz score.
Walah.
No.
Oh, okay.
Don't use MATLAB in this case.
Orang kau. Ini match base making nih. Langsung diskualifikasi kamu. Diskualifikasi. Apa ini? Nerf. Write them in increased orders unless they're complex, then put the real first. Huh? Oh iya.
Oh, actually, this is very easy, yeah.
Huh?
You don't have to compute at all, actually.
Masa?
Yep.
Really?
Why B? What's the reason? Yeah, Johan is correct. The answer is B. So I will add additional bonus for Johan.
Agak dapat nih,
Okay. Now, you see what kind of matrix is this? What is the type of the matrix?
Lower triangle.
Lower triangular matrix. Okay. A special matrix that we have for this kind of situation is diagonal matrix, upper or lower triangular matrix. For these three matrices, the eigenvalues are the diagonals.
Oh.
Yeah, the eigenvalues are the diagonals itself. Okay.
Lu cara tahunya gimana?
Yeah, upper triangle also.
Lu cara tahu?
He get it from the determinant. He's not using the upper lower triangular property. Yeah.
Determinant is 1.
Determinant is minus 1.
It's minus 1. Minus
Okay.
1. Determinant of this matrix is minus 1.
I'm still confused. Sir. How do you use the determinant to know the lambda value?
Say that again.
I'm still confused. How can you use the determinant to know the lambda value?
Use the determinant to know the lambda value. Okay, so we back again to the concept then, yeah. Let me repeat. We repeat again with this concept. Pay attention carefully. If we want to obtain non-zero x as the solution, then what is the equivalent condition for A? A inverse not exist.
Determinant equal to 0.
Determinant equal to 0. What else? Huh?
Not for
A not full rank. Okay, and etc. Yeah. To find out the eigenvalue, we are using this condition. Okay. Lambda is eigenvalue of A, x eigenvector of A, if this equation holds for non-zero x. Okay. For non-zero x, you don't understand the non-zero x, yeah? I can see your eyes. Yeah? Say it again. I haven't said about determinant yet for this, not yet. For this, I haven't. But for this one, I said already, yeah. For this problem to have a solution for x non-zero, then these are the conditions for matrix A. Okay. So lambda and x are eigenpair of A if this equation holds for non-zero x. Okay. And what are the conditions for this then? Use this. Then the condition is that A minus lambda I inverse exists or not? Not exists. Right? I'm just replacing A with A minus lambda. Okay, what else? Determinant of A minus lambda I 0. What else? Yeah, A minus lambda I not full rank. Not full rank. And etc. Now to find out the eigenvalue of A, the property that we will exploit is this property. Yeah, this property that we will exploit. Okay. When the determinant is 0, does it mean that the determinant is non-existent? It is just that the determinant is 0, right? It doesn't mean that it doesn't exist. Correct? Now, if the determinant of this is 0, can we explode the equation of the determinant? Can we do that? Yes, and then on the right side, the determinant of that is 0. And from this equation, we compute the lambda. Do you get it?
1 minus lambda times.
Yeah. Yes. Okay. Yeah, the only property that we can use easily is to use this property to find out the lambda.
maybe
Computing the inverse. If you want to compute the inverse of it, it is non-existent. We cannot use that property. Yeah, not full rank. Yeah, it's hard to use the non-linear dependency of the columns. It's hard to do that. Okay, because you will introduce another variable. Okay, non-linear independence of the columns. You have to prove that there are columns of A1 minus lambda. If you multiply with a constant C1, C2, C3, C4, okay, there will be non-zero seed so that it has a solution. Go back to here again. So we cannot use this property to find out the lambda. It doesn't mean that the property is wrong. The property is true, but we cannot use this. The only property we can use to find out lambda is this. Okay? Yeah, is this clear now? Okay, yeah. So Delon, does this answer your question? Why we use the determinant? Yeah. Yeah, it's the same like when if I'm saying that if I have a matrix A 3 5 minus 5, let's say like this, yeah. If I say that the determinant of this matrix is 0, what is the value of A? Can you do that? Can you compute that? Exactly the same thing, you compute this and this one. Okay? What's the value of A? Minus 3, yeah. If A minus 3, then the determinant of A is 0. Now you know. Yeah.
oh yeah.
Alright. Yeah, it's good if you ask this again so that we clear up all of the confusion, yeah. And anything else you want to ask? Up, ay. But what about this? Symmetric 3-diagonal matrix. This is not upper or lower triangular, so we cannot use the diagonal.
Why?
No more bonus, yeah. Bonus was only 1 just now. So you expand the determinant only for these two minor. Okay, you can get the determinant.
If the lambda is 0, then the eigenvalue doesn't exist.
If lambda is 0,
Then that's why I can.
no, the eigenvector exists.
Lambda 1.
Lambda 1 is 0, eigenvector exists.
But
Eigenvalue si lambda kan?
bukan
ya?
Oh,
lupa nih.
scaling factor.
If lambda is 0, then you only need this equation, right? The eigenvector is there. It's just that the A is singular. Okay, for that problem, you have 1 minus lambda, 1, 0, 1, 2 minus lambda, 0, 1, and 1 minus lambda.
Why?
Okay, find out what is the determinant of this.
Ah,
Yeah? So say it again. Yeah, determinant of this is 0. It is 0. It's correct.
Akhirnya,
Yeah, then we expand. What is this determinant?
determinannya
Yeah, what's the determinant? We expand it.
2 minus lambda kali.
So we use this, yeah.
Yeah.
It is 1 minus lambda multiplied by 2 minus lambda, 1 minus lambda, and then minus 1. I'm using the next,
Ya.
which is this one. So I have 1, 1, and 0, 1 minus lambda. Okay, 1, 1, and 0, 1 minus lambda. That's it. Yeah, the third entry is 0. 0 multiplied by anything is just 0. Yeah, it's gone. So I'm expanding from here to here and then there. Okay. Where's the minus again?
why is it minus?
Here one. This is the cofactor of the determinant. Cofactor of 1. You check on how to get the determinant from the chapter 7. There is a cofactor. You can label, yeah, for a 3 by 3 matrix. 3 by 3. The labeling. This is positive. This is negative. This is positive. Negative, positive, negative. Okay. It's like that. So what we have is 1 minus lambda. Determinant of that, this one, minus 1, multiplied by 2 minus lambda, 1 minus lambda, minus 1. And then minus of 1 multiplied by 1 minus lambda. That's it. Okay. So we have 1 minus lambda. Just 2. Minus 3 lambda. Minus 3. 2 and then minus 3 lambda plus lambda square minus 1 minus 1 plus lambda. Okay, so what do we have is lambda square minus 3 lambda plus 1 plus lambda minus 1.
Iya, cuma minus 1.
Okay, can anyone get this? This one?
Saat itu kita kalau
How is it?
langsung masuk ini langsung itu dulu cari gimana?
I will tell you how to get the lambda 3, yeah, from here. After this, I will show you how to get the lambda 3. Can anyone compute this? Can you get it for me? This one.
Ini tuh compute
I need-
lambda 1 lambda 2 as well, right? Huh?
I want you to expand up to lambda to the power of 3, lambda cube. What else? What else do we have?
Plus 3 lambda square.
plus 3 lambda square, and then minus lambda, and then this one again, and then plus lambda square again, plus 1, okay, and then plus lambda minus 1. So the result is that we have
Plus 4.
plus 4 lambda square minus 4 lambda square.
Minus 3.
Huh?
Minus 3.
Isn't it lambda here? Ah, 3. Minus 3, and that's it. Yeah. So what do we know from here? We can write down that this is as a lambda multiplied by minus lambda square plus 4 lambda minus 3. Okay, so it is explained here. The lambda 1 is 0, the next one is 1, and we need to find out what's the lambda 3 here.
Yeah.
So in this case, this equation can be written down as lambda times lambda minus 1 and lambda minus lambda 3. So what do you think the result would be?
Lambda minus lambda 3.
Yes,
3.
because the other lambda is 1, right?
No, 1. Yes.
Is there something wrong with that? Or it is lambda times lambda square minus 4 lambda plus 3.
Okay.
So lambda 3 must be 3 in this case, yeah. Lambda 3 must be 3.
Yeah.
So the equation becomes lambda
Lambda 3 harus 3.
plus 3, and this is equal to lambda minus 1 lambda minus 3.
Yeah.
Yeah, because we know that the first lambda is 0.
Oh.
This is 1, right? What's the next one? Is 3. Okay, yeah. Other question regarding this?
Kemudian ulangan sih. Oke.
Kalau disuruh invest lebih mati kan?
Yang nggak ada.
Itu masih still ini mas kalau disuruh invest gue up deh. 3 kali 3 di invest nih buat.
Yeah, lambda 3 is here, yeah. Lambda 3 equal to 3 is B. And another problem is also computing eigenvectors, which you can do on your own. And then when we come on Wednesday, we will discuss about this. And some of the problems also lah, we will discuss some of them. Okay. And also, I want you to find out the answer to this one, yeah. Show the proof. You said it's not true, yeah, Rafi. You check on using MATLAB. It is not true, yeah. Just now.
Ya,
It's not true. If it is not true, show the proof.